In this video lecture, we will go through what are colligative properties and then we will look at relative lowering of vapor pressure. Since we know that a solution is formed when say a solute, let's say solute here glucose, right, is added to water, we get a solute, right? So here in the previous video lectures we have understood that when in the lowering of vapor pressure, when we have gone through the lecture, we have seen that when a non-volatile solute was added to the solvent, right, that addition of that solute resulted into the lowering of vapor pressure of the solvent, right? Or we say that the vapor pressure of solution is less than that of pure solvent, right? So addition of this solute has resulted into the change in properties of the solution, right? Because the property of vapor pressure, right, has been changed by the addition of solvent, right? Similarly, we'll discuss this in later in future lectures. There are other properties like freezing point, right, or depression in freezing point, right, and relative lowering of vapor pressure, osmotic pressure. All these are properties that are associated with this solution, right? And when you add this solute, right, or any solute to the solvent to make a solution, then the properties of the solution will get changed by the addition of this solute, right? So we say that there are certain properties that depends on the addition of this solute, right? Or to be more specific, we say that there are some properties, certain properties of the solution that depends on the number of solute particles, right? Depends on the number of solute particles and not on the nature of the solute, right? So these properties are termed as colligative properties, right? I'll write it over here. Colligative properties, right, are properties that depend on number of solute particles added and not on the nature of solute, right? So we would be doing these colligative properties in detail, right? In this video lecture we will understand one colligative property, which is relative lowering of vapor pressure, right? So we would be going through these colligative property. First one is relative lowering of vapor pressure. The second is elevation in boiling point. The third is depression in freezing point. Fourth is osmotic pressure, right? Now let's just quickly, briefly just understand what these are. I said that when we have added solute to the solvent, right, earlier there were only solvent molecules at the surface, right? So when you added this solute glucose, this glucose will replace some of the solvent molecules at the surface, right, due to which the number of solvent molecules at the surface will reduce, right, because glucose molecules will reduce those solvent molecules, right? So now since we have less, right, since we have less solvent molecules at the surface, so what all things can happen, what all things will happen? First thing, since we have less solvent molecules, so less molecules of liquid will vaporize, right, or will enter into vapor phase, right? So less solvent molecules will enter vapor phase. Vapor phase. So what will happen due to this when less solvent molecules will enter into vapor phase? Your vapor pressure will decrease, right? Since less vapors are going into vapor phase, so vapor pressure will reduce, right? Due to less number of solvent molecules that are entering into vapor phase. Now, let's talk about boiling point. We know that boiling point, what is boiling point? Boiling point is temperature at which vapor pressure is equal to atmospheric pressure, right? Let's suppose this is your solvent, say water, right? And this is glucose. So when you heat it, let's suppose when glucose is not added, when you are heating pure water, so we have more number of solvent molecules at the surface. So more and more solvent molecules will move into vapor phase, right? And here we have atmospheric pressure, right? So when we have pure solvent, right, then more molecules of liquid will enter into vapor phase, right? And thereby increasing the vapor pressure, right? So when vapor pressure of this liquid will equal to the atmospheric pressure, liquid will start boiling. That is known as boiling point. And for water, it is 100 degrees Celsius, right? But now when we added solute to it, right? So solute, what solute will do, it will replace some of the solvent molecules. So now less molecules of solvent is available at the surface that will enter into vapor phase, right? So here now you have to heat this liquid more so that more molecules of liquid can gain kinetic energy and enter into and reach at the surface, and from the surface it will enter into vapor phase, right, to build the vapor pressure, right? And once the vapor pressure is of this solution, right, which is less than that of solvent, once this vapor pressure of solution becomes equal to the atmospheric pressure, then at that temperature your solution will start boiling, right? And that temperature would be higher than that of pure solvent, right? Why? Because pure solvent consists of only solvent molecules at the surface, but in case of solution you have less solvent molecules, so you have to heat this solvent to a higher temperature so that more solvent molecules can reach at the surface, and from the surface it will move into vapor phase to build the vapor pressure, and once that vapor pressure is equal to the atmospheric pressure, that solution will start boiling. So second thing we know now is that addition of solute will increase the boiling point. It will elevate the boiling point. So it will elevate the boiling point. We're going to do these properties in detail in next video lectures, right? Now let's talk about another property, which is your freezing point. We know that freezing point is the temperature at which your liquid will start changing into solid form, right? So freezing point is the point at which your liquid changes into solid form, right? And we know that the molecules of liquid are far apart, right, compared to solid, and molecules of solid are close and molecules of liquid are far apart. Suppose these are the molecules of liquid, so the molecules of solid would be close like this, right? So when liquid will change into solid, these molecules has to come close to one another, right? and since we are talking about freezing, and at freezing the temperature goes down, right? So at temperature at which this solid will change in this liquid will change into solid, that point is known as freezing point, right? And while freezing, these molecules of liquid, right, will come close to one another, right? These molecules will come close to one another, right, so that it can change into solid form. So while freezing, molecules of liquid will come close to one another, like this. These are molecules, so they will start approaching one another while freezing, right? This is how it will happen. These will start coming close to one another to make or to change into solid form as we decrease the temperature. Now let's take the case when you add a solute, a glucose to it. So when you add glucose to it, now let me show it with a different color. Here in this case there was no solvent, there was no solute, there was no glucose, right? So when you add glucose to it, these glucose molecules will come in between these liquid molecules, right? And they will produce hindrance, right, from these molecules coming close to one another, right? So these solute molecules will come in the way of these solvent molecules that are coming close together to form this solid, right, while freezing. So due to these solute molecules that are coming in way of these solvent molecules when they are trying to freeze, due to these solvent molecules, right, the freezing point, due to these solute molecules that are coming in way of solvent molecules, right, it will produce problem for these solvent molecules to freeze, these solute molecules. So you have to cool it, right, or you have to decrease the temperature further compared to the normal liquid so that this solution can solidify, right? So addition of solute will come, or addition of solute will cause freezing point to go down, right, which is known as depression in freezing point, right? This is your depression in freezing point. Why will it depress? Because solute molecules will come in between solvent molecules, right, that are trying to freeze, right? So this addition, so now we have seen two things here. In while boiling the liquid, by the addition of this solute, the boiling point will rise, right? This is known as elevation in boiling point. And at the time of freezing, these solute molecules will further lower down the freezing point. This is known as depression in freezing point, right? And this happened because of the addition of this solute, right? That the properties, that is depression in freezing point and elevation in boiling point, has changed, right? So the properties these two properties, depression in freezing point, right, and elevation in boiling point, these are colligative properties. Why? Because these properties depend on the solute added. Due to this solute added, the freezing point has gone down and boiling point has gone up, right? So these are colligative properties which depend on the solute added, or we say that depends on the number of solute particles added. So these type of properties that depend only on the number of solute particles added and not on the nature of the particles, these are known as your colligative properties, right? So if we just quickly look at one colligative property, lowering in vapor pressure. Lowering in vapor pressure is also a relative lowering in vapor pressure would be a colligative property. Why? Because it depends on the number of particles, solute particles, because when you add solute particles, it will lower down the vapor pressure, right? So these are colligative properties. Now let's take example. Let's take this example of this solution, right, where you add this solute, right? We have x2 is equals to mole fraction of solute, right, and this is your solvent, right? This is x1 is the mole fraction of solvent, right? Let's take n1 as moles of solvent, right? n2 is equals to moles of solute, right? We have done this before also, right? So when you add solute to this solvent, some of the molecules at the surface will decrease of solvent molecules, because these solvent molecules would be replaced by this solute particles, right? So that will result into lowering of vapor pressure above this solution, right? So we know that mole fraction x1 is equals to mole fraction of solvent is equals to number of moles of solvent divided by the total number of moles in the solution, which is n1 upon n1 plus n2. Similarly, mole fraction of solute would be number of moles of solute divided by total number of moles in the solvent, right? And we know that as per Raoult's law, we have done this in the previous lecture, the vapor pressure above this solution, this is equals to P0 into x1, right? P0 into x1. P0 is vapor pressure of pure solvent, P is vapor pressure of solution, and x1 is mole fraction of solvent. And we know that vapor pressure of this solution is directly proportional to the mole fraction of solvent. We have already done this in the previous lecture, right? If you have any doubts, you can check the previous lecture. And one thing we will show you now here, we said we know this thing that P, right, P is equals to vapor pressure of solution, right, and P0 is equals to vapor pressure of pure solvent, right? And by this understanding, we know that vapor pressure of solution is less than that of pure solvent. P is less than P0. If you look from this relation of Raoult's law, right, x1 plus x2 is equals to 1, right? Sum of mole fraction, right, is always equal to unity 1, right? So x1 would always be, x1 would be 1 minus x2, right? x1 is equals to 1 minus x2. So x1 would always be less than 1, right? So if you put here P is equals to P0 x1, right? If x1 is less than 1, if this is less than 1, then P is less than P0, right? Say if x1 is less than 1, then P is less than P0, right? So we have also seen this now mathematically, right? That P, which is vapor pressure of solution, is less than P0, which is vapor pressure of pure solvent, right? If you want to take just example, you suppose I said if x1 is less than 1, suppose x1 is equals to half. If I put the value of x1 here, p0 half, right? So p0 is equals to 2 times of p2, right? So from here we can see that p is less than p0, or p0 is greater than p, because p0 is twice of p, right? This is simple mathematics. Now, since I said that P is less than P0, right? So lowering in vapor pressure, which is, right, I said that P is less than P0, right? So addition of solute has caused lowering in vapor pressure, right? So what is lowering in vapor pressure here? Let's say lowering in vapor pressure is delta P. This would be equal to P0, which is the vapor pressure of pure solvent, minus P, vapor pressure of solution, right? And if I put the value of P from equation 1, it would be P0 minus P0 x1. It would be P0 1 minus x1, right? So 1 minus x1 from here, x1 plus x2 is equals to 1, right? So it would be P0 x2. So the relation is equals to P0 x2, right? So this is your lowering in vapor pressure. If I bring it here, this P0, this is lowering in vapor pressure relative to pure solvent. If I write it like this, P0 minus P upon P0 is equals to x2. So this is your relative lowering in vapor pressure, and this we have proved is equal to mole fraction of solute, right? So this is relative lowering in vapor pressure is equal to mole fraction of solute, right? Because lowering in vapor pressure is caused due to addition of this solute, right? So now it's clear from this relation that relative lowering in vapor pressure is equal to mole fraction of solute, right? This is your mole fraction of solute, and this is your relative lowering in vapor pressure, relative lowering of vapor pressure, which is equal to mole fraction of solute x2, right? Now we know that x2, if we calculate the value from here, right? So x2 is equals to, x2 is mole fraction, and we know that mole fraction from the above formula is n2 upon n1 plus n2, right? So now I'll put the value of x2 from here, right? So P0 minus P upon P0 equal to, if I put the value of x2, it will be n2 upon n1 plus n2, right? And we know that n1 is the number of moles of solvent, which n1 would be very much greater than n2, right? Because for dilute solutions, n1 quantity, that is the moles of solvent would be very much higher than that of solute, right? N1 is very much greater than N2, right? So since N2 is very less, so we can ignore N2, right? We can ignore N2 here. So we can write this as is equals to N2 upon N1, right? And for any dilute solution, we know that P0, which is the vapor pressure of pure solvent, and the number of moles of solvent is constant, right? For dilute solution, P0 and N1 are constant, right? So these two are constant. So we can write it as P0 minus P, right? is directly proportional to N2. N2 is the number of moles of solute, right? So this is what we have to prove. From here we proved that lowering in vapor pressure is directly proportional to number of moles of solute, right? Which proves, since the lowering of vapor pressure depends on the number of moles of solute, that is the number of solute particles, right? So this is your colligative property, right? This proves, since lowering in vapor pressure depends on the number of solute particles added, right? So what do we call to the properties that depends on the number of solute particles added? We call these properties as colligative properties, right? So this proves that it is a colligative property. Why? Because lowering in vapor pressure is directly proportional to number of moles of solute, right? So it's a colligative property, and from this colligative property you can calculate the molecular weight of the solute, right? If I put the value of, we know that number of moles of solute, number of moles is equals to weight upon molecular weight. If I put weight upon molecular weight here, I can calculate the molecular weight of solute, right? P0 minus P upon P0 is equals to N2, that is W2 upon M2, right? Now N1 is W1 upon N1, right? So from here M2 can be calculated. So therefore M2 would be equal to P0 minus P upon P0, right? I'm sorry, M2 would be P0 upon P0 minus P, right? W2 upon W1, right? And M1, which is the molecular weight of solvent. So if you know the molecular weight of solvent, right, and weight of solvent and weight of solute, and weight of solvent, and these quantities, you can calculate the molecular weight of solute that is added and which resulted into the lowering of vapor pressure, right? So we proved that relative lowering of vapor pressure is a colligative property, and from this relation we can deduce the molecular weight of your solute that is added, right? So I hope all this is clear to you. And one more thing to mention here is that relative lowering in vapor pressure is a colligative property, right? Lowering in vapor pressure is not a colligative property, right? Lowering in vapor pressure is not a colligative property because it does not depend upon the mole fraction of the solute. It's the relative lowering in vapor pressure that depends on the mole fraction of the solute added. This is a colligative property, but lowering of vapor pressure is not a colligative property, right? So now we have proved all this, right? So this formula is important. You get numericals on this, right? So I hope all this is clear to you. Thanks.